Welcome to AP Statistics Chapter 11 review. Chapter 11 is all about inference for categorical data. We've done quantitative data with significance tests. This is a test for categorical data, and it's going to be the chi-squared test. So this is basically what chi-squared is. This is how you write it. That's the test we're going to be using. And basically what chi-squared is, like I said, testing for categorical data like color or not number, basically. So it's divided into 11.1 and 11.2. 11.1 is for one variable and 11.2 is for two variable. We'll get into the technical terms later. But without further ado, let's get started. So the first section is chi-square test for goodness of fit, which is for one variable. And we're going to be using what's called a one-way table here. And a one-way table, basically, it only has one variable, let's say color. The example we'll be using mostly is going to be the color of graphing calculators, because graphing calculators are very important in AP statistics. We have blue, red, um, green. Let's go with black, and then white. The only reason I wrote out black is because we already used B for blue. And we have these five different values. And let's say they should be all be the same because the same number of each color was made. And you want to test out if that's true. So how are you going to do that? One way to do it is to do a significance test on blue, then on red, then on green, then on black, and then on white, and see what you get. If that proportion is equal to zero point 0.2, because zero point 0.2 is the proportion that all are the same, 0.2 times 5 is 1. If it's equal to 0.2, then it fits our hypothesis. But that runs into a lot of error because, first of all, you are doing the same test 5 times, which is bound to get boring at some point. But also, it increases the probability of a type 1 error because it's 0.05 for the first test, but you just multiply by 5 because you're running 5 of those. So 0.25, it's pretty likely that you're going to make a type 1 error, especially if you have something like 20 different colors. You're practically guaranteed to make a type 1 error. But that's where chi-square tests come in. You can do a bunch of data at once. So the observed counts are basically what you're given. Let's say there are 11 blue calculators, 8 red calculators, 11 green calculators, 13 black calculators, and 7 white calculators. So if you add that up, you're going to get a total of 50 calculators, which is a nice round number. Let's say you got this data by you went into your school, asked each person what color their calculator was, and you got 50 people's responses, and these were the colors. Um, those are the observed counts. The expected counts are what you expect. And since our proportion that we expect is 0.2 for each, we can't just use that. We always have to use counts and not proportions for chi-squared. It's observed counts and not observed proportions. So you might be thinking, well, if this is 0.2, we can just do 11 divided by 50 and get a proportion and just do that for each of these. Not really. You're going to want to do counts because that's what chi-squared is all about. So 10, because you're just doing 50 divided by 5, 10 in each. That's your expected. Now that we have that, let's move on. What are our hypotheses going to be? Our null hypothesis generally is going to be something in the form of the stated distribution is correct. So in this case, the company's calculator distribution is correct. They state that all of it's the same, so we'll test that out. The alternate hypothesis is going to be it's not correct. And sometimes you can say at least two of the proportions are incorrect. The reason we're not saying one is because if one is incorrect, that means something else has to be incorrect as well for that to balance out, since they all have to equal one. So usually you can just write it's all correct, it's not correct for the alternate hypothesis. Now we can finally calculate what's called the chi-squared statistic. So to get the components of the chi-squared statistic for each value, you're going to be doing the observed minus the expected squared over the expected. So if we do the first one as an example, you do 11 is the observed, minus 10, 1 squared divided by 10. That's a pretty easy example. You get 0.1. Not that big of a deviation. Our worst one is 13 and 7. So we can do 13 minus 7 is 6 squared. Sorry, 13 minus 10 because the expected is 10. 13 minus 10 squared is going to be 9 divided by 10.9. Even the strongest deviation isn't that bad. Maybe the company's claim is true, but we have no way of figuring that out until we actually run the test. So I will show you how to do the test on your calculator. But before we do that, we need to talk about the distribution. So I'm gonna just actually I'll bring back the data because we're gonna be calculating it in the future. But I just wanted to clear space to draw the distributions. So chi-square is not like a normal distribution where it's just the same shape throughout. It just varies in a mean and standard deviation. Instead, it looks pretty different. When the degrees of freedom is 1, it looks like that. When it's 4, it looks like that. And this is from the textbook, actually. It's always going to be right skewed, but as degrees of freedom increases, it's going to get closer and closer to looking normal. And this is obviously a really bad representation of chi-squared, but it works for this thing. It just is always right skewed, becomes more and more normal, and the area to the right of a certain point always increases as degrees of freedom increases. And like I said, degrees of freedom, but how do we calculate that? Instead of sample size minus 1, it's not going to be 49 in this case. It's actually going to be 4. It's the number of categories minus 1. And since we have 5 categories, that's going to be 4. Now, the p-value of the chi-square distribution is going to be calculated using something called chi-squared CDF. Now, we're not there yet. What we haven't done is calculated the actual chi-squared statistic. That's just a component of the chi-squared statistic. What you're going to do is you're going to add up all the chi-squared statistics that you collected from all the data. If you add it up, you get 0.1, 0.4, 0.1, 0.9, 0.9. You could calculate that by yourself, but you're going to get a total chi-squared statistic of 2.4. Then you go to chi-square CDF, you go to distributions and chi-square CDF, not PDF. There's also PDF, but you're not going to be using that. Now, why don't you use normal CDF? It's because it's a chi-square distribution. And if you click on chi-square CDF, you're going to get a box or a window that asks you for the chi-squared value. We have 2.4. And you're also going to need to input in the degrees of freedom. So here we have 2.4, and it's going to ask for a lower and upper bound like usual. Lower bound is going to be 2.4, upper bound is going to be infinity or a really large number. Degrees of freedom we said was 4. You're going to get a p-value of 0.663. That's our p-value. Now, what does this mean exactly? This we can write a conclusion now. We basically say because p equals 0.663 is greater than the alpha value of 0.05, there is not convincing evidence that the distribution is incorrect. Basically, we fail to reject the null hypothesis. So that's for goodness of fit. And we solved our mini example here. But I didn't really explain how to do it the calculator way. Before we do that, we should talk about the conditions on doing this test. Usually we do that before, but I just wanted to get the example over with before we do this. We have random condition. So the random condition basically says that it was taken from a random sample. And 10% is that the sample size is less than 1/10 of the population. Large counts basically says that all expected counts are larger than 5. This is where it's different. The expected counts is going to be 10, 10, 10, 10, 10 for our distribution. If each of those is greater than 5, then we can run the test. If for some reason one of them was like 4, then we can't run the test. It's too small. And then there's something on your calculator called the chi-square goodness of fit test. You can just plug in your data into a list, and then plug in that list into the test, and it'll do everything for you. But you're still going to need to write it down on the actual hierarchy. Follow-up analysis is something you can do as well. You find out what's the biggest component. A component is basically part of the chi-squared value, one part of it. And I mentioned this before. The biggest was 13 and 7. They both were the same. You would just write that in your follow-up analysis. The biggest contributors were, I believe that was black and white. The black and white calculators had a chi-squared of 0.9 each. And you would just write that. Now, was our value expected? We got something like 66%. It was pretty expected because those values weren't too far away from the expected value of 10. Just 11, 8, 11, 13, 7. Those are not very different. So it makes sense that we got that. Okay, moving on to 11.2, which is inference for two-way tables. A two-way table is basically a table that has two variables. So it's going to be like a matrix. For example, you could do color of the calculator and type of calculator, like TI inspired, TI 84, TI 83, and then black, blue, white, red, green over here. That is one way to do it. Usually it's going to be something more distinct, like the color of the calculator and the class they're in, AP Calc, honors pre-calc. That really doesn't matter much. I guess a better example would be type of calculator, TI inspired TI 84, and name of class. Maybe people have more TI 84s than 83s in AP Calc because it's a harder class, and so on. But that's what a two-way table is. I'm not going to draw one because it's a pretty big table, and yeah. We have observed counts and expected counts. Expected counts are a bit different this time, though. Expected counts, it's going to be the row total, or the column total times the row total divided by the entire total, or the total. So if you have the value 31 here, and you basically add up everything in this column, you get 60. You add up everything in this row, you get 50. And the entire total is going to be, let's say, 800. It's going to be 60 times 50 divided by 800. That's a pretty drastic example. But you get an answer, and that's going to be your expected count. And you would do that for every single value. You don't really need to because your calculator can do it for you when you're inputting in your matrix and then doing the test. It will generate the other matrix with expected counts as well. There are two different tests, one for homogeneity and one for independence. Homogeneity is when there are different samples for the thing. So an example, let's say in a restaurant, we have the type of music and the entree order. So this is one from the textbook, actually. But it has the data. They had different samples, right? Obviously, you can't play all the music at once in one sample. Instead, on one day you play French music and you collect data for that. One day you play Italian music and you collect data from that. So they're different samples, meaning it's homogeneity. Now, the hypothesis is going to be there's no difference in the true distributions, and there is a difference in the true distributions. The degrees of freedom and conditions. So the degrees of freedom is going to be row minus 1 times column minus 1. So in this, if you have 3 rows and 3 columns, it's going to be 2 times 2, which is 4. And that's going to be your degrees of freedom. And conditions, it's going to be the same 3. Random, 10%, and large counts. And they're actually going to be the same conditions, just slightly varied. Random means random samples because it's multiple samples. 10% each sample size has to be less than 1/10 of the entire population sizes. And large counts, all of the expected counts have to be greater than 5. All right. Now we can finally do the chi-square test for homogeneity. I'm not going to do an example for this because it's pretty similar to that of the goodness of fit. And also we're going to be doing an example with two-way tables in the soon. But basically what you do here is you're going to enter in the matrix and then just do chi-squared two-way test or chi-square test, depending on what calculator you have. That's going to give you an answer. Or you can just manually calculate all the chi-square components, find the chi-square statistic, use chi-square PDF, so on. Sorry, chi-square CDF, and so on. The second type is for independence, and this is when there's only one sample. For example, let's say you're collecting data about whether students like the college or not, and it's just one sample, but you do record if they're male or female. So male, female is one variable, gender basically, and whoops. The other variable is whether they like it or not. They like it, they don't like it, they don't have an opinion, and so on. So it's still one sample, but they have two different variables. So the reason why it's independence is because now you can tell whether or not male and female, like the gender basically affects whether they like the college or not. And same test, actually, same test you would do, but it's a little different. The hypotheses are going to be different. Instead of there's no difference, it's going to be there's no association between these two variables, and the alternate is going to be there is an association. For degrees of freedom, same thing. It's going to be row minus 1 times column minus 1. Conditions are the same, random 10% large counts. And this is going to be the chi-square test for independence, not homogeneity. It's called something else, but practically the same thing because you just input the same thing into your calculator. You just get a different conclusion once you get your p-value. And the follow-up analysis, same. So what's the format for writing a chi-square test? We want to test at the alpha equals blank level, usually 0.05. You write your alternate and your null and alternate hypothesis. If conditions are met, we will conduct a chi-square test for either goodness of fit, homogeneity, or independence at the alpha equals blank level. You do your conditions, random 10% large counts, and then you have your calculations and finally your conclusion. Along with your calculations, don't forget to include a graph with your chi-square. Because when you calculate the value, you're gonna press draw, so you get a graph, and you just copy that graph onto your paper. So our example is actually from an actual FRQ, but all this question asks is to name the hypotheses or name the test and the hypotheses and not actually calculate anything. But I wanted to use it to calculate things. So that's why you don't see a question stem over here. All you have is the background info. Basically, what it's saying is soft drink, if they drink a soft drink in the past week. So for 3 different cities, and then yes or no, and they give you your totals too. So what you're going to do is determine whether or not, well, let's see what you're going to do. It says 3 independent random samples. So is it going to be homogeneity or independence? It's going to be homogeneity because it's 3 different samples. So instead of saying there's no association, there's no difference, meaning there's no difference between the true distributions for the cities. So you can go through the entire FRQ writing process, but I'm just going to briefly go over it. Our null hypothesis is going to be there's no difference, and our alternate is going to be there is a difference. You're going to have to write the entire thing, obviously. This is going to be a chi-square test for homogeneity, and since they didn't specify, it's going to be alpha equals 0.05 level. As for the conditions, random, yeah, 3 independent random samples, good. 10%, I'm assuming there's going to be at least 9,000 people in Baltimore, 16,000 in Detroit, and 22,000 in San Diego. So then you test the expected values. You could do it on your calculator, basically. To calculate, you first do the test on your calculator, and then you see if the conditions are met, which is a valid way of doing it, just to get the expected values table. So that's what we're going to do. I'm going to show you how to use the calculator thing. So on your calculator, when you go to stat tests, there's going to be chi-square test. Instead of chi-square GOF, which is goodness of fit, you're going to just go to chi-square test. And you're going to enter in your matrix. So you would have typed that matrix in usually A earlier. And you're going to get an answer. You don't even need to type in degrees of freedom or anything. You get you can see your expected value matrix in matrix B usually, and you look at everything's at least 5, and it makes sense because they should be approximately similar to these values, and all of those are much greater than 5. So now you actually do the test. and you get degrees of freedom is equal to, well, it's a 2 by 3, so it's going to be 1 times 2, which is 2. So your degrees of freedom is 2. Now you would calculate the chi-square statistics for each one. On the paper, you would actually write out the first few chi-square statistic components, then just do plus dot 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 and get your final answer from when you do the test on the calculator. This one, you're actually going to get a pretty high value. I won't tell you right now, as you can just do it on your own first. So feel free to pause the video and try it on your own. You're going to get a chi-squared of 86.490 approximately. And then you use chi-square PDF, or you just look at what you got from your calculator, and you're going to get a p-value of 1.656 times 10 to the power of negative 19. And your calculator might just say 0 for this because it's basically 0. It's 10 to the power of negative 19. And you would draw your graph. Since degrees of freedom is 2, it looks something like that. And then 86 all the way out there, and then just very small area shaded in. So that's going to be your answer. Now you just write your conclusion. Because p is approximately 0, which is less than alpha equals 0.05, we reject the null hypothesis, and there is convincing evidence of a difference in the true distributions between cities. That would be your answer. And then answer any follow-up questions if it asks for a follow-up analysis of the components and that's actually it for this video. It was pretty brief because chi-squared is sort of like a repeat of previous units. It's just different names for things, different names for tests, statistics, and things like that, which is why I didn't go too in detail on how to write the FRQ. It's very similar to previous ones. So that's it for chi-square, chapter 11. Chapter 12 will be next, and that's more about regression. So see you next time.